This video will focus on arcs and chords and the relationship between them. So as we go through, we're going to walk through a handful of theorems that are in the textbook. And as we go through, think about how you would go about proving them. We're going to talk about what they are, what they mean. We're really going to break down the meaning of each theorem. But as we go through, think about how you would prove them. Let's start with theorem 10.2. So what theorem 10.2 says that in the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. In other words, if I look at this circle, and it's the same circle, if I look at chord AB and chord XY, what this theorem is saying is that if these two chords are the same length, then their corresponding arcs, so in this case arc AB, must be the same as arc XY. And remember, that's an if and only if, which means that it has to go both ways. So if I start with, say, the chord AB being congruent to chord XY, that would tell me that arc AB has to be congruent to arc XY. And that goes both ways. If I start with the arcs, that also has to get me back to that the chords are congruent. So if I'm writing a proof for this, I'll have to start with one, get to the other, and then start with the first, get to the second. So you'll in essence have to write two proofs on this one. So be thinking about that, think about what that really means. Okay, let's look at theorem 10.3. If a diameter or radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. In other words, if we're looking at this situation here, where AB is a diameter, so that'd be part of my hypothesis, AB is a diameter, and XY, which is a chord, is perpendicular to AB, which we've represented with the right angle there. This would imply, and remember this is only a one way, that if we mark this point, let's call it Z, XZ is congruent to ZY, and arc AX is congruent to arc AY. So on the picture, we can say that this segment is cut in half, XY, as well as saying that this arc AX is the same as AY. So be thinking about how you would prove that. Think about where you would make your triangles to try and start proving these things. Start with perhaps a radius coming from C to X and C to Y, and then we can make some triangles and try and prove that it's first a perpendicularly bisected chord and then go to the arcs, probably using central angles. If we look at theorem 10.4, the perpendicular bisector of a chord is a diameter or radius of the circle. This one's very similar to 10.3. It's just a little bit different. So the idea is I get to start with both AB being perpendicular to XY, and I know that both of these are chords at this point. I don't know that AB is a diameter yet. And I also get to start with, if I mark this point again as Z, I can say that XZ is congruent to YZ. Now using that, I would have to deduce that AB is a diameter. So I have to prove that it goes through the center of the circle C somehow. Now this one's a little bit more involved, it's a little bit inventive, but again we have to make triangles and think about how we would do it. Again, we would probably use central angles. We could even possibly use contradiction here as a means to prove this. But in essence, if I can show that AB and XY are perpendicular and that the segment is cut in half by AB, I can deduce AB is a diameter. You can use that in your homework, but be thinking about how you would prove this theorem come test time. Okay, there's one more theorem in this video that we're going to talk about, and that'd be theorem 10.5. And in the book it says, in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So this one again is an if and only if, and what it's saying is that if FG as a chord is congruent to AB as a chord, this can only be true if the distance, which we're representing with segment XC, notice that it's perpendicular up here, and likewise, we're noting this is also perpendicular between CY and AB. So if XC is equidistant to CY, this goes both ways, since it's an if and only if. If I know that they're equidistant, then I can say that the chords are the same. If I know the chords are the same, then they must be equidistant from the center of the circle. Now again, we can use this in the homework, but be thinking about how you would prove it.